take it away. Thank you.
Thank you very much. So hello, everyone. Today I'm going to tell you about the recent cosmology analysis with the kilodegree survey, also known as KiDS. We recently analyzed 1,000 square degrees of the data from this survey, and in this image, in these two stripes, you can see how this data looks like. So this is showing a two-dimensional density distribution over the two stripes. So the lighter parts are showing where you have more higher density, and the darker parts where you have lower density, white, for example. So there are two stripes, but the positioning of these stripes is not correct on the sky, although their length is correct with respect to the background. So they don't actually go through the Milky Way. So KiDS is a weak gravitational lensing survey. So it's a probe of the large-scale structures. And we analyzed the weak lensing data, but we also combined it with spectroscopic data from other surveys to set tighter constraints on cosmological parameters. And here I will show you some results from our recent analysis. Okay, so when it comes to cosmology with KiDS, the main probe is cosmic shear. And here you can see with this cartoon, I will tell you how it works, what are the basics of it. So imagine you have a galaxy that is far away from the observer, and its light passes by large-scale structures and massive objects, and as a result, it is distorted. So now if you observe the image of this galaxy, it's going to be different from the intrinsic shape of the galaxy. Now imagine you have two such galaxies in the background, and their light passes by similar structures, so they're similarly distorted, creating a correlation between the shapes that are observed. And this correlation is what we measure as the cosmic shear signal. Now, to model the signal, we need to know how far away these galaxies are, because if they're further away, there's more matter along the line of sight, and there should be more lensing happening. So we have two main ingredients. One is measuring the shapes of the galaxies, and the other one is to know how distant they are, and for that we use lensing. For that we use Redshift. And obviously you need to have some sort of model to be able to tell what's the matter distribution along the line of sight and what kind of signal you expect to get. Okay, so this is like just a cartoon version of how cosmic shear works. And before I show you the results, I want to tell you a little bit about KiDS. So it's a weak lensing specific survey, meaning that the quality of the image is very high, and that's very useful for getting the shapes of the galaxies accurately. So that's the first ingredient. And then we have 9 photometric bands, which we use to estimate the redshifts. This is a bit special about KiDS, because when you combine KiDS with its sister survey, Viking, you get 9 photometric bands, which is more than the number of bands you get with other surveys in general. And that helps with getting better estimates for redshifts. In general, when we do lensing, we don't have the spectra of each galaxy because that's too expensive to get, and we want to go to higher redshifts. So we want to have many galaxies. So we use photometry, and photometric bands give us some idea of where the redshift is, but they're not like super accurate. So if there are more of them, you can get a better like understanding of where these galaxies are. So we've analyzed 1,000 square degrees of data, as I've said, which includes 21 million galaxies. And this is after all the masking. And the survey is now completed. We have an extra 350 square degrees that we're analyzing now. All right, so the results that I'm going to summarize today are based on these 6 papers that form the core cosmology analysis of the KiDS-1000 data. So the first three papers are showing the cosmology results. First one is cosmic shear. Second one is combination of cosmic shear with spectroscopic surveys, so the combined probe analysis. And the third one is showing what happens if we use extensions to standard model in our analysis, because the first two are assuming that you have the standard cosmological model, which is flat lambda CDM. And then we have the methodology paper, which describes the methodology used in the first three. And then the last two papers describe the two main ingredients of the analysis: the photometric redshifts, how they're measured, and what are the tests we've done on them to make sure that they're correct. And then we have the shear measurement that tells us what the shapes of the galaxies are, and all the tests done on that part of the data as well. Now, you're welcome to read the papers if you want to get more information. But if you're someone who prefers to watch the film rather than read the book, then you can go to YouTube, to the Kids Consortium page, and there is a playlist there with all the kids talks, so you can get a bit more information than what I can give you today. All right, okay, so let's first start with cosmic shear. So here in this plot, I'm showing the data vector for cosmic shear. We did our cosmic shear analysis using 3 sets of statistics. So these are all 2-point statistics, and they're all looking at things like correlations between the shapes of galaxies, but in different spaces. So this one I'm showing you here is the real space 2-point correlation functions. You have psi plus on the top, psi minus on the bottom. And the reason I'm showing this one out of the 3 of them is because if you are familiar at all with any of the cosmic shear analysis, then you've probably seen a plot like this in one of the papers. So these are like the traditional statistics used for cosmic shear. Although they're not the best ones, they have some limitations that don't make them very attractive for this analysis. Okay, so the data vector we have is quite massive, as you can see. And this is because we divide our galaxies into redshift bins to get the evolution of matter through redshift. So each of these panels is showing correlations between shapes of galaxies in 2 of these redshift bins. So Z11 is showing the autocorrelation of shapes in bin 1. And for example, Z15 is showing the cross-correlation of shapes between bin 1 and bin 5. And bin 1 is at lower redshift, bin 5 is at higher redshift. So one thing you can see from this plot is that there is a trend that the signal increases as you go from left to right and top to bottom. And this is because when we go further, we go to higher redshift bins, most of the galaxies are at higher redshift, so there's more matter, intervening matter, and the lensing signal is therefore stronger. So you can see the theoretical model, the best fitting model drawn with the red line. And this model includes several sections. The first bit is the cosmological part. We use the flat lambda CDM standard model. And then we have 2 groups of nuisance effects that we also include. The first group is looking at the impact of basically modeling the impact of astrophysical effects. We have the intrinsic alignments of galaxies, and we have the effect of baryon feedback. And then the second group is looking at observational nuisances. So we have the uncertainty in calibrating photometric redshifts or calibrating the shear or the shapes of the galaxy. So the 2 main ingredients of the analysis. All right, before I show you the money plot, which you probably have seen, I just want to give you a little bit of a backstory about why we obscure the data and why we do basically blind analysis. So there is a longer story before that, but I'm just going to start with the previous kids data. So the previous KiDS analysis used 450 square degrees of the data, so it's a bit less than half of what we have now, and found that there was a mild tension between our data and the cosmic microwave background analysis of Planck data. This was at a level of 2 sigma or so. But at the time, Planck had collected all their data and there wasn't anything they could do to improve their statistical power. So the ball was in our court, and we had to establish if this tension will increase or decrease if we increase the statistical power. So it was very important how we were going to do the rest of our analysis. And one aspect that can really affect this sort of thing is the subconscious biases of the researchers. So in order to make sure that we don't apply our own subconscious biases to the analysis, whether or not we wanted it to match with Planck or not, we obscured the data. Okay, so and here's where we were 3 weeks before submitting the papers. So we have 3 sets of blinded data, and this plot here is showing constraints on S8 versus omega m. Omega m is the matter density parameter, and S8 is the parameter that characterizes the amplitude of the lensing signal. So higher S8, more lensing from the same matter, from the same model. And so what you see here is that you have the CMB Planck contours. This is in red, and you have the 3 blinded contours here. So one of them is the truth, the other 2 are fake, but we don't know which one it is. And we're doing an unblinding party to find out which one it is. But before we did the unblinding, we did a poll to see what people want to be the truth. And you can see here, most people wanted it to be blind B, which means that we would have a tension similar to the H0 tension. So this is of order 4 sigma or so. But there were people who preferred to not be in tension and chose blind A, which is less than 2 sigma. So it's like 1.7 or something. So it's not really tension. And then blind C is living happily in the middle. But it turned out to be blind C. So it's a bit ambiguous, but it is a 3 sigma tension. So let me just tell you first what these plots are showing. So on the left-hand side, you have constraints on sigma 8 and omega m. Omega m, as I told you, is the matter density parameter, but sigma 8 is showing how much matter clusters, or is the amplitude of the power spectrum. We have 3 contours for cosmic shear, and these are the 2-point statistics that I told you. So the first one, the blue one, is showing the 2-point correlation functions. That's the plot I showed you before. These are real space quantities. And then in Fourier space, we have band powers, that's shown in pink. And then we have Kusabi's, which is in neither space, but it has some properties that make it very attractive for this kind of analysis. And that's why that's our fiducial statistics for this paper as well. Now you can see that the cosmic shear contours are all elongated. And this is the Planck contour here, the red one. And this kind of elongated contours are called cosmic bananas. And this degeneracy between sigma 8 and omega m exists in all cosmic shear analysis. And that's because with lensing alone, we cannot tell between a situation where you have a lot of matter, but this matter is not very clustered, versus another situation where you have a little bit of matter, but this matter is highly clustered. And because this degeneracy exists, we usually look at this other parameter called S8, which is defined here. It's a combination of sigma 8 and omega m, but it varies across the banana. So it's roughly perpendicular to the banana. So it varies this way. And now if you look at S8 versus omega m, you can see that the Planck contour is above all the R contours, and R contours are consistent with each other. And this is about 3 sigma. Okay, so now there's another way to look at the same data, and that is just to look at a parameter that's similar to S8, but now we call it capital sigma 8. The only difference is that the power here is fitted to the banana. So now capital sigma 8 is exactly perpendicular to the banana. And you can see that if you use SABs or band powers or two-point correlation functions, you get different values for alpha. So their degeneracy direction is not exactly the same. So the first line here is showing the Planck constraints for capital sigma 8. And the other 3 are showing values for R analysis. So one thing you can see here is the size of the error bar fit in Planck and the size of our error bars are quite similar. So we're setting competitive constraints on this parameter. We also wanted to see what's the impact of the nuisance effects that I introduced earlier on our analysis. So number 5 to 12, they're looking at the impact of the observational nuisances, and 13 and 14 are looking at the astrophysical ones. So you can see that there isn't very much difference when you turn things on and off or you change some of the priors on them. The only biggest difference is with baryons. So if there's no baryons means no baryon feedback. So if you turn off baryon feedback, you can get a little bit of a shift, which is larger for the two-point correlation functions because they're more sensitive to smaller scales. Aside from that, we wanted to see what's the impact of each of the redshift bins in our analysis. So we had 5 redshift bins, redshift bin 1, low redshift, bin 5, high redshift. So what we did was to remove each of the bins and all their cross correlations from the analysis and redo the analysis with the rest of the bins and see what happens. I can see if you remove bin 1, 2, and 3, then not much happens to the constraints. It doesn't really matter which one you're looking at, which one of the panels you're looking at. While if you remove bin 4 and 5, you get shifts that are much more significant. And now you can understand this as the effect of signal to noise. If you remember in the plot I showed for two-point correlation functions, the signal to noise for the first few bins was much lower than the last 2 bins. So if you remove each of the last 2 bins, then that's almost equivalent to removing half of your data. So then it shouldn't be surprising that you get these shifts. But we weren't happy with just like looking at this, and we also did a fully Bayesian analysis to see if any of these shifts are statistically significant. And it turns out that bin 4 and 5 are completely in agreement with each other. But this test actually flagged out bin 2 as being an outlier. Now, as you can see, bin 2, if you include it or not, doesn't really make any difference to our constraints. So for completeness, we just kept it in our fiducial analysis. Okay, and we can compare our results with previous cosmic shear results as well. Here, we're going back to S8 again, because we can't really use capital sigma 8 in a consistent way between different analyses. So if you look at S8, we have our R analysis results in the first 3, and then the cosmic shear results from previous analysis in green from 4 to 7. Number 8 is again showing the Planck results. So number 4 is showing the previous KiDS results. So this is the 450 square degrees analysis. And then 6 and 7 are showing 2 are results from two competing surveys. This is dark energy survey and hyper-SuPrimeCam. And then number 4 and number 5 is showing a combination of the reanalysis and a joint analysis of the combination of this and the previous KiDS data. So what you see here is that our results are consistent within themselves, but they're also consistent with previous cosmic shear results. And the size of the constraints we have is the smallest compared to any one survey. But perhaps most interestingly, what you see from this plot is that all the points are on one side of what Planck estimates. So it's not just that we see the 3 sigma tension. If you combine the different probes, you're going to see the tension still being there. Okay, so we see tension with cosmic shear, but we can use other probes of the large-scale structures as well. So with cosmic shear, we're looking at correlations between shapes of galaxies, but we could also correlate positions of galaxies to get galaxy clustering. So galaxies are tracers for matter, and they tell you their distribution tells you what the underlying matter distribution is. And then there is a third probe, that's the combination of a cross-correlation of cosmic shear and clustering. With that one, we're looking at the cross-correlation between shapes of background galaxies with positions of foreground galaxies. And this is telling us what's the matter distribution around the foreground galaxies. And this is what we did. So here, let me tell you which surveys we used. In the 2 top stripes, you can see the KiDS footprint, KiDS North and KiDS South that I show at the start. And then we have BOSS in blue. This is the one of the spectroscopic surveys that we use. And you can see it has overlap with KiDS North, but it doesn't have any overlap with KiDS South. So for KiDS South, galaxy-galaxy lensing, which needs overlap between the 2 samples, we use 2DF lens. And 2DF lens is another spectroscopic survey, which is quite similar to BOSS. Okay, now I'll show you the results when you combine cosmic shear, galaxy clustering, and galaxy-galaxy lensing. So again, we're looking at constraints for S8 and omega M. Cosmic shear contour is in pink. It's the band cover contour. And then almost perpendicular to it, we have galaxy clustering. That's the blue contour. And if we combine it with galaxy-galaxy lensing, we get the purple contour. And you can see the purple contour is slightly smaller than the cosmic shear one, but it's not really adding very much information. Now, if we combine all 3 of them, we get the red contour. And you can see the Planck contour in gray on top, and we're still stuck with the 3 sigma tension. So what the clustering data provides is degeneracy breaking between sigma 8 and omega M mainly. So we can look at the sigma 8 omega M plane now, so we don't have the banana anymore. And the red contours still are combined probe analysis results, and the gray one is Planck results. But now we have 2 other sets of contours. These are looking at results from other analysis that used similar methods. So the blue one is combination of BOSS. This is BOSS data release 12, plus the previous KiDS data. And the orange one is looking at the dark energy survey year 1 combined probe analysis that used their own data. And you can see our contours are consistent with the other combined probe approaches analysis, but we're still inconsistent with Planck. And it looks like from this plot that the tension is mainly driven by the value of sigma 8 rather than omega M. Okay, so we have we still have this tension between parameters between the value of S8 between Planck and large-scale structure analysis. So let's look at other models to see if we can alleviate the tension. And this is what we did in the extended cosmology paper. We looked at a number of extensions, but none of them managed to reduce this S8 tension by very much, aside from the wcdm model. The wcdm model is very similar to lambda CDM, just has an extra parameter that allows the equation of that governs the equation of state for dark energy. So it allows dark energy to vary with time, basically. Now this plot here is showing constraints for different parameters. You have the S8, sigma 8, omega m, you have W and H. But I want you to look at this panel on the left. So this is marginal distributions for S8, and just look at the gray and the orange one. So this is comparing Planck with the combined probe analysis. Now if you look at these two, there isn't really that tension between them. This is like below 2 sigma, basically, the difference between these two. So it looks like maybe wcdm is doing something useful. But if you look at another panel, for example, W versus SA, you see that the two contours, the orange and the gray, are still separated from each other. And this is about 3 sigma or so. So all it's done is to move the tension from one parameter to another one, basically. Okay, so this is the first part of my talk, and I have actually 2 questions for you. And if you want to ask me questions about this part, I think this is a good time to do it as well. And then we see how we get on and how much time there is, and then I can go to the second part. So my questions are, which parts of this analysis are the most interesting or controversial to you? And what do you think the tension between KiDS and Planck means?
Go ahead.
Sorry.
Yeah, go ahead, Alkistis.
The most interesting for me is how much you trust your nonlinear modeling, and if a theoretical systematic that still might be in the nonlinear modeling could be responsible for that tension, or instead, if you think it is more traditional systematic like PhotoZis or something like that, have you checked that? And what do you do with baryons in particular? Do you let them vary or do you fix them?
Yeah, thank you for that question. Actually, I'm going to go back to this plot because I haven't really explained what each of these are, but I think that will make things a bit clearer. So if we're thinking about the nonlinear modeling, what we're using as fiducial nonlinear modeling is using HM code, which has baryon feedback included in it. And baryon feedback is basically calibrated against hydro simulations. So what we've done here in number 13 is to set baryon feedback to 0 to see what happens. And you can see that you don't get a very big change for these two, but you get a, like, I don't know, 1 sigma shift for this one, this panel here. And we can understand why this is happening. It's because psi plus psi minus, they have a very broad kernel. And even when you limit your angular ranges, it's still sensitive to smaller scales where baryon feedback is important. So they are impacted by that part of the nonlinear matter power spectrum. But these 2 other statistics, because we've limited their range, they're not really sensitive to baryon feedback. So this is showing that our results are not that sensitive to them, basically, whatever way you might model them. And the other systematics, so number 5 to 12, we're looking at anything that could be reasonable, within reason could be the case. Especially, I want you to look at number 12. Number 12 is we're setting all uncertainties in the calibrations to 0, so there's no uncertainty. And then you can see that we're not really impacted by it. So we could have just like ignored all of these nuisance parameters and would have gotten basically the same result almost. And in the other ones, we're like checking what happens if we increase the error on the photometric redshifts, or if we increase the error on the calibration for shear. So you can see like what happens. M is the shear calibration, sigma Z is the photometric redshift calibration. And you can see that the shifts are within what we expect. It's nothing unusual happening, basically, any of them. So I think I'm happy with like the level of control we have on the systematics, basically. Okay, that answer your question? Did I miss part of it?
Yes, thank you.
Yeah.
But I also imagine, maybe also for people who don't have experience with this, that also all these things, the results are very signal to noise ratio dependent, right? If you had a survey that was 10 times better, probably these shifts would look very different. So
yes, that's true.
Yeah, the low, no, KiDS is great, but if I imagine like LSST or something like that, I could also imagine that these 1 to 20 cases could look very, very different.
Yeah, that's true, definitely, because they have to worry about like percent level errors, but we don't have to really.
Yes, thank you.
Is anyone else brave enough to answer Marika's questions?
Oh, yeah, I'll bring the questions again if you forgot them, whatever.
Don't be shy.
If you have like a theory you think that would fit this as well, come forward. All right, I guess if there is nothing else, I'll go to the second part of my talk. Okay, so this second part, I'm going to just talk about parameter estimation and their interpretation. But this is a bit more general, so it applies to any likelihood analysis. So if you ever want to do a likelihood analysis, you have to take these things into account. I'm going to give examples of what we've done, but it applies to a lot of other disciplines as well. And these are things that we learned during this analysis, basically. So these were new for us, which means that it will probably be new for some of you as well. All right, so the first one is the impact of priors on your analysis. So basically, the takeaway here is that you need to be careful with informative priors. So the example is cosmic shear analysis. These two plots are showing prior range in red and the constraints in blue. We're looking at the prior that was used in the Desier 1 analysis versus their constraints on the right-hand side, and the prior that was used in the previous KiDS analysis, and the prior and their constraints on the left-hand side. So the first thing to look at is the panel that's showing sigma 8 versus omega m. So it's this panel and this panel here. Now, the thing with the prior is that if you've ever used a Boltzmann solver, a class or COM, you have probably noticed that you need to set this parameter AS. And AS is the amplitude of the primordial power spectrum. Now, AS doesn't translate directly to sigma 8, which is more low redshift quantity. So if you, once you translate your prior on AS or log AS to sigma 8, it will have a weird shape like this or like that. So that's the red contours. Now, if you look at the sigma 8 versus omega m panel, you see that the contours that are the constraints from data, their length is basically dictated by your prior. So if your prior is tighter, you get a smaller cosmic banana. And then that might make you think that you have tighter constraints, while this is just a prior effect. Okay, so that was the first one. And then the second one, I want you to look at the panel for S8, just S8 itself, so these two panels. And here you can see that the prior, again, translates in a non-trivial way to the value of S8. So you have, basically you have an informative prior on S8, which decreases very sharply for higher values of S8. Now, luckily, for the range that we're interested in, so between like 0.6 and 0.9, the prior is relatively flat in both cases. So it shouldn't affect our constraints very much, but this is just a lucky coincidence, basically. So for the KiDS-1000 analysis, we decided we are not going to go through the route of putting priors on AS. Rather, we're going to put priors on S8, because S8 is the parameter we care about. So we put a flat prior on S8, so it's not informative, over a very large range. And that's that basically actually produces contours that are slightly larger than either of these two priors. Right, so that's the first one. And then the second one is, how do you actually interpret your results once you have done your, say, MCMC chain or multiness or whatever. So this is an example from a mock data analysis. So in this example, again, you see sigma 8 versus omega m contours. But what's happening here is that your contours don't match with your input. Your input is shown as dashed lines, but your contours seem to want some value that is different. Like it's a higher value for omega m, lower value for sigma 8. So what's happening here? So we first thought maybe we've done something wrong in the analysis. And by the way, this is noise-free analysis. But then soon we found out that no, this is not something we've done wrong with analysis. It's just interpretation that is not correct. Because we're looking at marginal distributions, and the likelihood distribution is not Gaussian. We have informative priors on some of the parameters. We have hard edges. This can impact the marginal distributions in a non-trivial way. And in this case, which is a combination of cosmic shear from and galaxy-galaxy lensing, we get a very strong effect, basically. But if we look at the full posterior distribution and then look at the maximum of that distribution, we get something that recovers the input, and that's the star here. So after seeing this, we decided that we're not going to report marginal distributions or any of the properties of the marginal distributions as our fiducial result, although we still reported it because everyone does that. And instead, look at the properties of the full posterior distribution. And this is summarized here. So this is again the same contours, and the star is the same. But the question was, how do you set an error on this star? Because you can't really use the same error as you had for your marginal ones. And this method we came up with, which is called, we call it projected joint highest posterior density interval. So that's shown in the red, as red. And this is done by kind of ordering your posterior values going from the highest value to lowest, and then seeing how many of these points you have to include until you get 68% of your parameter, like 68% of omega m or 68% of sigma 8. And that, by definition, includes the input value, because that is captured by the maximum posterior, so the star. So this, I think, is very important, because it's also when you are thinking about tensions between parameters, if you have a case that's like this, that can make you think there is tension while there is not. All right, so that was the second one that I want to talk to. And then the last one I want to take you through is how do you actually get the goodness of fit for your model? Because that's another thing you need to always think about. Does my model actually fit my data? How good is the fit? And now here the example is again cosmic shear, and this is mock data. So we have 500 realizations of the mock data. So this is noisy data. Noise is taken from the covariance. And in the data vector, we have 120 data points. And we're varying 12 free parameters. Now the question is, what is the degrees of freedom? Because we need the degrees of freedom to translate the chi-squared to a goodness of fit. So what's the degrees of freedom? Is it the number of data points minus the number of free parameters, or is it not? So on the plot, you can see the distribution of minimum chi-squared values for these 500 realizations. And let's see if we use the degrees of freedom based on this formula here, do we get a distribution that corresponds to the minimum chi-squared distribution? This is what we get. And you can see that it's just like by eye, it's obvious it doesn't really match the data. And you can see the p-value for this fit, it's very poor. So it's obvious that the number of free parameters we're using is not correct here. And this can be understood. If you think about it, we have 12 free parameters, but a lot of them are degenerate with each other, and a lot of them have informative priors. So we don't actually have 12 free parameters. They're just like mildly free. So what is the number we should use? So what we can do is instead try to fit to this distribution and see what effective number of free parameters we get. And if we do that, we get this black contour, which gives us, I think, 7 parameters or something here. Okay, but we can also try to estimate the number of free parameters from our posteriors. And this has been done for recently, like looking at something called dimensionality, which is basically looking at the standard deviation of your chi-squares in your full posterior, or some other property of your full posterior distribution. This is just to basically to avoid going through modeling 500 realizations, because that takes a lot of time. And if you do that, you can get values that are closer to your actual values. So this is the red curve versus the black curve, but still they are not representative. And it really depends on your priors and what case you have, really. So in conclusion, what you can do is basically what you need to do for a likelihood analysis is to take care of your priors and try to set priors that are uninformative, at least for the parameters that you care about. And then if you want to calculate degrees of freedom, the best way is to use mock realizations of your data. But if that's not possible, you can try to estimate it from different properties of your posterior distribution. But you have to make sure that you take into account that these are just estimates and that if you're just using one chain to get the estimate, you have the noise from the chain as well. So your estimate is going to be noisy. All right, so as getting to the end of my talk, I'll just summarize here. So we see a 3 sigma tension in the value of S8. This is assuming flat lambda CDM and comparing it with data from Planck. From the combined probe analysis, we can see that this tension is driven by the value of sigma A, so which means that the universe is less clumpy than Planck predicts. This result is validated using mock KiDS and past galaxy surveys, which I didn't talk about, KiDS image simulations and null tests, spectroscopic photometric clustering analysis, and all identified uncertainties, systematic uncertainties are folded through as nuisance parameters. And lastly, watch out for your priors. And I'll end with a picture of KiDS. This is before lockdown and also during lockdown. Thank you.